Well, myself, Dr. Ganesh Shinde. I'm going to talk about nuclear magnetic resonance spectroscopy, which is going to be a very handy tool in the hands of an organic chemist. Let me just go over with some basics of this NMR technique. Yeah. So NMR mainly consists of it works with a hydrogen nuclei and hydrogen nuclei. So it comes with a two spin quantum number with a plus of and minus of. They normally are degenerate in their energy level, and however, when they are put in the external strong magnetic field, so they get bifurcate themselves into two different energy level. So wherein plus half gets aligned to the external magnetic field and get lower in energy, whereas the minus half get opposing to the applied field and get the higher energy. And yeah, before going with that, I think I need to tell about some of the other magnetic nuclei and their uh, whether they are magnetic nuclei or not. So if you just look at the some of the values over here, that is here is a proton, okay, and it is a deuterium as a hydrogen, and deuterium hydrogen is having a nuclear spin quantum number as I as a half value. The concept is any nuclei with a non-zero spin value will be magnetic in nature, and one can see the values that goes with a half, 1, 0 and all these things. Those which are having a spin value as 0, so they are non-magnetic nuclei. Okay, so one can see the spin value as a half, and if it is a half, then there can be two spin states, and if it is a 1, as in case of deuterium, so then it's going to have three spin states. And normally we focus more about the proton NMR as well as the C13 NMR. So they come to the help of an organic chemist, and let us look into that in the next slide. Okay. So yeah, this is the slide I'm just would like to tell about. So not in a, when the protons are not in an external magnetic field, both the protons with a plus of and minus of, these are the intrinsic property of these protons, and nothing can change this intrinsic property. So they are at a degenerate energy levels, but however, when they are put in an external magnetic field, so then there exists a nuclear magnetic resonance. Okay, so this is the applied external magnetic field, and yeah, this N and S that represent the external magnetic field. And when the proton is put in the external magnetic field, okay, so then proton in the sense hydrogen nucleus. Okay, so they get the degeneracy is lost, and they get themselves, okay, in a two spin state they get aligned in the external field, and those with the plus of they get aligned, and those with the minus of they get unaligned, and those unaligned will be of higher energy, and those with the aligned they are of the lower energy than with the normal barrier. So now the energy gets separated, and now if you by any means if you supply the energy, the right amount of energy, the energy that is equivalent to this difference in amount in these two states, and then you can just think of the transition from lower energy to the higher energy level. So that is being done by radio frequency region of the electromagnetic radiation, and that is the essence of this NMR, which is called as a nuclear magnetic resonance spectroscopy. That means the applied magnetic field will make a bifurcation of these protons into plus of and minus of spin states, and then by absorbing the right amount of energy that lies in the radio frequency region, so then there can be a transition, and that leads into the absorption of radiation or the radiation. And of course, always the higher energy state is unstable, and it comes to the ground state by emitting out the energy of the same kind, and that is recorded in the recorder device, and that gives you a signal. Okay, so the signal tells you about the magnetic nuclei, and of course there are a lot of things in this technique, because the chemical environment is going to affect, and that gives a lot of good information in the this particular technique. Let us see to that in